Last week we worked on truth table method to determine the validity of an argument in chapter 13. We will continue to work on chapter 13 this week too, and also next week. Chapter 13 just contains too many materials, so we will spend 3 weeks to work on chapter 13. This week, we will work on a method called proof. And this method is also for determining the validity of an argument. So you may ask why we need another method to determine the validity of an argument. We already know truth table method to determine the validity. Okay? So why do we need another method? Well, the answer is this. When it comes to the question about the validity of an argument, ordinarily, we use the method of proof to persuade others that an argument is valid. If someone does not see how the conclusion follows from the premises, we first indicate that some premises lead to an intermediate conclusion, which then leads to another intermediate conclusion, and so on, eventually to the conclusion. That is, for example, suppose you say, well, you believe that C. Okay, let's see. You say your belief or conclusion is, let's say, C. Okay, and someone asks, well, why C is true? Well, your friend asks why he or she has to accept C. Well, you say C is true because P1, P2, P3. Let's say. You say, you try to give reasons why C is true. You try to provide ground for believing C. But your friend asks again, well, I don't see how P1, P2, P3 justify C. Or your friend asks, he or she doesn't see how the conclusion follows logically, validly from the premises. So the question arises about whether the given argument is valid or not, and you think that the argument is valid, and the other party doesn't believe that. What can you do? Ordinarily, we do not sit down and construct truth table to persuade others that a given argument is valid. That's not what we do ordinarily. Okay? What we do ordinarily is, well, if you don't see that C follows from P1, P2, P3, what you do is you guide the person step by step. Okay? You tell the person, well, even if you don't see immediately that C follows from P1, P2, P3, don't you see that P1 and P2 justifies C dash, okay? C prime, okay? If the person says, well, I can see that much, then you say, well, don't you see then that from C prime and P3, C double prime follows. And given that C double prime, don't you see that C follows? Something like this. Okay? You try to kind of build a bridge between the premises and the conclusion. Kind of build a bridge, okay, from between premises and the conclusion that helps the person to see that the conclusion, after all, logically follows from the premises. And providing such intermediate steps that connect the premises and the conclusion is called proof. Okay? That's what we do ordinarily. And in logic, we just learn how to do that in a systematic way. So, here is the definition of proof. To provide a proof of an argument is to construct intermediate steps that connect the premises and the conclusion. Okay? Now, here is the important thing. Only by using fixed rules of inferences, okay? When you construct the intermediate steps, you must rely only on the rules that are agreed upon. Okay? If you appeal to rules of inferences that are themselves controversial, then your demonstration would not be as successful as you wish. Okay? So, we will learn what are the accepted rules of inference in the following. Okay? So, we will spend some time to go, step by step on the rules of inference. Okay? And then we will come back to actually constructing a proof. Okay? The first one is called simplification. Okay? In short, SIMP. Okay? The rule just says this: when you have a conjunction statement like P and Q, the rule says you can derive P. It's that simple. Okay? You can derive Q as well. Okay? Because it says P and Q. What does that mean? P and Q means P is true and Q is true. So it gotta be true that P is true. Okay? So this pattern, okay, this is called the rule of simplification. Conjunction is more like the opposite of simplification. Okay? Here you kind of move from conjunction to its component. Here you move from component to a conjunction. Okay? So when you have P, Q separately, you can derive P and Q. You should find these rules obvious, okay? Almost trivial. Okay? Of course, if you have P, if you have Q, you can say P and Q. That's trivial. Okay? But that's the point. Okay? There is nothing controversial here. There shouldn't be. Okay? All the rules that we will lay down here are the rules that what logicians think everybody will agree. Okay? And we will use only these rules in constructing a proof. So the third one is called addition. This rule is useful but a bit tricky. It says when you have a statement, you can add any statement. Q is really, maybe it's not appropriate to P, to say Q. Because addition rule really says when you have P, you can derive P or whatever. Okay? You can add any statement whatsoever, and still it's a valid rule. And you can see that why this is valid. Okay? Because P or Q, a disjunction statement is true if only one of them is true. Okay? So we know that Q is true because P is true. So no matter what comes in the second part, P or star, the whole thing has to be true. So given that P is true, P or star has to be true. So it's a valid inference. Okay? The next one is called disjunctive syllogism. It says either P or Q is true, and you learn that one of them is not true, then the other got to be true. Okay? Remember that in these rules, PQ doesn't stand for just PQ. Okay? For example, suppose you have like Q and R, or let's say T. And you have, say, negation of Q and R. Okay? Negation of Q and R. Then you can derive, in virtue of disjunctive syllogism, you can derive what? You can derive T. Okay? This is a legitimate application of DS. DS says you have something or another, and you have negation of something. Then you can derive the other, T. Okay? So I think it's less misleading to maybe write down the rule DS by saying, well, something or another and negation of one of them, then you can derive the other. Okay? Maybe this is less misleading. Okay? So what matters is really the pattern of argument. Okay? All right. Let's move on to the next one. Hypothetical syllogism is concerns sentences, conditional sentences. It says P then Q, Q then R, then you can derive P then R. Okay? It moves like that. Okay? Hypothetical syllogism. It says HS. Okay? These two rules we will use quite frequently. Okay? It says if P then Q and P is true, then we can derive Q. Modus tollens says P then Q and not Q, then we can derive not P. We already have talked about these rules before. And you should remember these rules. I mean, we will use these rules quite often. Constructive dilemma. You have two conditional statements like that, P, Q, R, S. And it says P or R, then you can derive Q or S. Okay? That's constructive. Destructive dilemma. The conditional is same, okay? The conditional sentences are same, but instead of P or R, you have not Q or not S, then you can derive not P or not R, okay? Like that. I mean, you just have to familiarize yourself to these patterns, okay? So whenever you see these patterns in a concrete argument, you should be able to see the pattern and say, well, I can derive this by using the rule such and such. Okay? Now, rules of equivalence. Before we start this, what is called rules of inference goes in one way. Let's go back to this. All rules of inference that have been introduced so far have this characteristic. If you have these premises, you can derive that. So it really goes from goes in this way, okay? Only one way. In contrast, what's called rules of equivalence goes both ways. For example, double negation. It's a rule of equivalence. It says P is logically equivalent to saying not P. Again, it's obvious, okay? To say P is saying the same thing as it is not the case, then not P. Okay? The difference between rules of inference and rules of equivalence is that rules of equivalence goes both ways. So when you have P, you can derive not P. But also, when you have not P, you can derive P. So rules of equivalence allow going both ways. Okay? That's a big difference between rules of equivalence and rules of inference. The next rule of equivalence is tautology, what's called tautology. It says to say that P is basically saying the same thing as P or P. Again, P is the same thing as P and P. Okay? So when you have P, you can derive this. When you have that, you can derive that. Okay? Remember, tautology is only limited to or and and. P, if and only if, P, if P then P. Okay? This is not tautology. Okay? When the sign is or and, you have tautology. Okay? Not when you have conditional statement like that. Okay? Commutation says you can switch these two components again when you have or and. Okay? That means to emphasize, you shouldn't do this. Okay? When the statement is conditional, commutation rule doesn't apply. Okay? When you say P then Q, that's not the same thing as Q then P. Okay? No, that's not a legitimate rule. Okay? You have a commutation. Okay, you can switch around only when you have wedge or dot. Okay? Associative rule says, again, associative rule works for and or, not for other connectives. That's true for other rules as well. Associative rule is when you have P dot Q dot R, you can move parentheses, okay, front or backward. Okay, so you can move parentheses to the front and says P dot Q dot R. Okay, that's the same thing. Okay. You can say the same thing for wedge statement. You can move parentheses forward and backward. Okay? That's associative. It's really like, it would be useful to think of a mathematical formula. Like when you have 2 plus 3 plus 5, that's the same thing as what? 2 plus 3 plus 5. So it's like that. Okay? We have similar of pattern in logic. Okay? Distribution. You distribute. Okay, when you have and or like or and, you can distribute P to Q, P to R. Okay, so you distribute P to Q and have P dot Q, and you distribute P to R and has P dot R. Okay? Watch out for the connectives here. Okay? You distribute and sign, okay? And basically it becomes a wedge statement. Here again, you distribute P to Q and P to R. Okay? That's called distribution rule. Implication rule is tells us how to change a conditional statement into disjunction statement and backward. Okay? It says to say that if P then Q is saying the same thing as not P or Q. Okay? This is very useful rule. Okay? Implication. Contraposition rule says if P then Q, to say that is saying the same thing as you switch these two, but you add a negation sign in front. So P then Q is saying the same thing as not Q then not P. Okay? That's called contraposition. De Morgan's law, DM, allows you to remove the bracket, parentheses. It says there is a negation sign in front of parentheses, and you can remove the parentheses, but by distributing the negation sign to each of them. But remember that in De Morgan's law, the and sign changes to or sign changes to and. Okay? So when you remove the bracket, parentheses, you distribute negation sign to each of them, but have to change and to or to and. Okay? Exportation says P dot Q then R is this, logically equivalent to P then Q then R. Okay? So when you have that, you can derive this. When you have that, you can derive that. Okay? Biconditional rule tells about this biconditional sentence. Okay? This is what? It means P if and only if Q. P is necessary and sufficient condition for Q. Now what that means is if P then Q and Q then P. Okay? P is both sufficient condition for Q and necessary condition. This is also equivalent to this. Okay? What this says is P, both of them, PQ, both of them are true, or both of them are false. If you look at the truth table for P if and only if Q, you remember it says PQ, T, TFF, TF, TF. P if and only if Q is true when? When PQ are, both of them are true, or both of them are false. Only in these two cases, P if and only if is true, otherwise false. So this rule reflects that. Okay? P if and only if Q is true when both of them are true or both of them are false. Only in these two cases, they are true. So the rule, biconditional rule. Okay? Again, when you have that, you can derive either one of these two, or you can go backward. Okay? Okay, we are done with all the rules of inference and equivalence. Let's do just one exercise problem. So given all these rules introduced so far, well, how do we actually proceed to construct the proof? Let's say here is an argument, okay? In constructing a proof, you number premises first. So what that means is you do this, okay? One, first premise, okay? Two, not Q. There are two premises. You write down the conclusion here to kind of remind you that that's the final destination that I have to reach. Okay, so the starting point is these two. Okay, the goal is I'm going to show that we can start from these two premises and construct intermediate steps only by using the rules that have been introduced so far, and we will finally reach the conclusion. Okay, that one. Okay, we have not reached that yet, but that's the goal that I hope to reach. Okay. Okay. So we have to fill in the intermediate step, and the next step we number 3. Okay. What I do is this. I look at the premises and go over all these rules and try to see if there is any particular rule that can be applied in this situation. Okay. Let's see. What I can do here is this. I look at this and I think that I can add not Q or not R. Okay, because look at the rule addition. The rule addition says I can add any statement whatsoever. Okay. By wedge. So this is from number 2, and I have used the rule addition. So whenever I complete a step, I write down where I get that. Okay, where I get that from. Okay, I got number 3 from number 2, and by using the rule addition. Okay. So the number of the previous step used and the rule that is appealed to. Okay. 4th step. And I see that I can use the rule De Morgan. Okay. From I can derive Q dot R from number 3. So it's a number 3, and from number 3, and I use the rule DM, the Morgan rule. What's next? Now, whenever I try to think about the next step, I kind of look at all the previous steps and try to think of what rule can be applied to any statement or any pair of statements. In constructing number 5, I think that I can, there is rule that I can apply to number 1 and number 4. Number 1 is what? Basically, disjunction statement. something or another. Okay? Number 4 says, one of them is not the case. Right? Says something or, okay, something or another. And number 4 says, one of them is not true. So I can derive the other, right? So I can derive here, not P. What is the rule that allows me to do that? That's a rule called what? Disjunctive syllogism. Okay. So number 5 is derived from 1, 4 by using the rule disjunctive syllogism. Okay. Now, that is the conclusion. Okay. So once I have reached the conclusion, a step that is identical to conclusion itself, I stop there. Okay. That completes the proof. There are some instructions, tips that are given, that are explained in the book about how to, what are the things that you need to look for in constructing proofs. When it comes to constructing a proof, there is no royal road. Okay, you have to just sit down and do problems. Okay, you have to exercise. Okay, so that's it for today.